Welcome to the examples video for lecture 2 on big and small. I'm at the point in making videos where I can't remember if I did this in our original video, so I'm just going to walk through this example. All right, so let's say that we were given this very, very large number. Okay, and we want to put it into scientific notation instead because this is pretty gnarly to have to write out every single time. Okay, so remember that we want to start our answer to this problem with just one digit to the left of the decimal. So I'm going to say, okay, well then that means that this is going to be 6.02214. And this is definitely going to be times 10 to the, but we need to know now what goes up here, right? So in order to figure that out, I just remember that, okay, well, in a number like this, the decimal point is actually right here. So then I'm going to count how many times I would need to move the decimal in order for it to end up over here, between the 6 and the 0, okay? So I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Okay, so since I had to move the decimal 23 times, I'm going to put a 23 as my exponent. Okay, let's try another one together and I'll go just a little bit faster through it. Okay, so let's do another one. This one is going to be just a little bit smaller. But again, we want to start by writing our answer with just one digit to the left of the decimal. So this answer is going to be 7.92. And then now we just need to count how many times we move our decimal to get it over to our ending spot. That's 10. So this is 7.92 times 10 to the 10th. Okay, so remember it's the exponent number, not the base number 10, but this exponent number that corresponds to how many times you move the decimal. All right, so with very, very, very small numbers, like very, very small decimal numbers, we will want to format our answer the same way that we did with our large answers, right? So we'll want to make sure that the beginning of our answer has the first digit just to the left of the decimal. So it'll be something like that. So we want to write it as 9.10939, okay? And then we need to count how many times we move the decimal. But since we're kind of like moving it to the right, remember that we are denoting a very, very small exponential number, okay? So however many times we're moving that decimal, it's going to correspond to times 10 to the negative, and then this number ends up being how many times we move that decimal, okay? So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 24, 25, 26, 27, 28, 29, 30, 31. We had to move that decimal point 31 times. And then, of course, remember to write the units of your answer. Okay, so 9.10939 times 10 to the minus 31 kilograms. See, did we get it right? Yes, we did. Okay, let's also do the second one. So again, we want to have the first non-zero digit just to the left of the decimal. So this is going to be 8.8 times 10 to the negative, again, because negative exponent means this is a number very, very, very small. And so then now we just count how many times we have to move that decimal. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 8.8 times 10 to the negative 13th, and that's milliliters. Did we get it right? Yes, we did. All right, so for this first example, how many grams are in 26 kilograms of M&Ms? Well, let's go back to the previous slide to remember how many grams are in a kilogram or how many kilograms are in a gram in the first place. All right, so this information, remember, tells us that there's 1 kilogram for 1,000 grams. Okay, so if we page forward, okay, well, if 1 kilogram is 1,000 grams, then 26 kilograms must be 26,000 grams. No problem. Okay, so then what about how many millimeters are in 2.3 centimeters. This one's a little bit more tricky. Okay, so here's centi and here's milli. And so then we see that, well, there's 100 centimeters for every 1 meter, and there's 1,000 millimeters for every 1 meter as well. So then clearly the centi is 10 times larger than a milli, but we're starting to get a little bit twisted. So you could just kind of recognize that, well, there's 1,000 millimeters in every 100 centimeters, and then you could just say, oh, well, so let's say 2.3 centimeters must then correspond to 23 millimeters. All right. But this is where we start to get just a little bit, like doing those back of the brain sort of quick relationships can start to get a little bit messy, and it starts getting very easy to do it wrong. So this is where we start needing to use what we call the factor label method, which you probably saw me use once we got to the moles conversions and so on. Okay, so what we really know for sure is that there's 1,000 millimeters in 1 meter, and there's 100 centimeters in 1 meter. And so what I think is the safest thing to do is to relate the centimeters to a meter, and then relate the meter to 1,000 millimeters. Let me show you. Okay, so we know that we're starting off with 2.3 centimeters. That's what we've got. And we want to know how many millimeters that corresponds to. So we know how many centimeters are in 1 meter. It's 100. So why don't we convert the centimeters into meters? So I will say, so let's see, if there's 100 centimeters equal to 1 meter, then we can say that, so let's see, these two cancel out to just give us the answer of 1. And so then we have this fraction that is still true. We can also do it the opposite way. We can say 100 centimeters is equal to 1 meter, but then we can divide both sides by the 100 centimeters. And so then these two cancel out, and then we're just left with 1 is equal to 1 meter over 100 centimeters. Now, why the heck would we want to do that? Because we're also going to use fraction relationships to get out of centimeters and into units of meters. So let me just show you the right way to do this first. I'm going to use this fraction. I'm going to multiply it by the quantity that I've started with, and I'm going to multiply by 1 meter over 100 centimeters, which is the same thing as saying 2.3 centimeters times 1 meter divided by 100 centimeters. Okay, and so then you'll see that the centimeters on top and on bottom cancel out thanks to fraction rules. And so then that leaves us with, well, 2.3 times 1 is just 2.3, and then divided by 100, that comes out to 0.023 meters. That's how many meters we've got. Okay, but then let's bring it back to what we really want. We really want to be in millimeters. So now we say, okay, well, let's take those 0.023 meters, and let's see, how many millimeters are in a meter again? Oh yeah, it's 1,000. Okay, so we're going to use the same idea here, but instead we're going to say, okay, well, I've either got 1,000 millimeters per 1 meter, or I've got 1 meter per 1,000 millimeters. So now what do you think? If I want to get into millimeters and end up with millimeters on top and no meters anywhere, which of these two fractions should I use? That's right. We want to use the top one. Oop, come back. All right, so I'm going to multiply by 1,000 millimeters divided by 1 meter. And even though I'm not going to show this spot here, the same process still applies, okay? So because of all of this stuff, this truth here, now we can just say, oh yeah, I've got this guy on the bottom, so it cancels out this guy on the top. So then 0.023 times 1,000 equals 23 millimeters. Okay, and so you may ask yourself, well, if I already knew how to do it the fast way, why would I ever want to do it the long way? And the answer is because there are going to be much more complicated practice problems that I'm going to be asking you to do as part of this class. Okay, so for example, let's jump forward to the moles problems. Okay, let's work through this example together. Okay, so we know, so you may be wondering, okay, where do I even start? And so again, let's focus on what we definitely know, a quantity that we know, not a relationship between two conversion factors that we know, but just the quantity that we are given in this question. And that quantity is this one, the 7 micrograms of carbon, okay? And so then the answer that we're trying to get to is carbon atoms, okay? So, but let's start with just the 7 micrograms, 7 micrograms of carbon. Okay, so what else do we know? We know that we need to get to, well, let's see. Hopefully in the last video, I gave you the typical flow that we use to get from mass of an element into atoms of an element, and that is that we go from mass to moles and then to atoms. And that mass, really, we have to be in grams. And how do we get there? We have the grams to moles relationship, which is really the atomic mass of that particular element. Okay, and then to get from moles to atoms, we always use Avogadro's number, which is 6.022 times 10 to the 23rd, things per mole, or really just atoms per mole. Really, it's going to be things, and you'll see why in a few weeks. Okay, and remember that this number, Avogadro's number, you always use it no matter what your element or what your item is. Okay, but remember that the mass to moles relationship is really grams to moles relationship. Okay, so do we have grams yet? No, we are stuck in micrograms. So what we need to do first is we need to get into grams from whatever other mass unit we are stuck with at the beginning of the problem. So we need to page back a couple of slides and remember that 1 gram is going to be equal to 1 million micrograms. Okay, so now we can start our problem. So we'll start with micrograms, but we're going to get right into grams. And since we want to get into grams, we've got to put the grams on top, and we're going to put the 1 million micrograms on the bottom. Okay, so now you could just give an answer right here and then have it be in grams. Or instead of going through all of these intermediate steps where you get like this answer and then this answer, you can just kind of trust that like multiplication just kind of works in the steps that you do it, even if you don't get the intermediate answers or write down the intermediate answers. And so instead of stopping every time, what you can do is you just start to string the conversion factors you're going to use together. So now that we've used this 1 gram to 1 million micrograms conversion, I'm going to still cross out the micrograms to remind myself that, okay, once I actually do divide 7 by 1 million, that answer is going to be in grams now. Okay, so now that I'm in grams, my next step is to get into moles. Okay, so how do I get there? I need to use the grams per mole number, and maybe I'll use it like that, or maybe I'll flip it upside down. Okay, so I need to go to my periodic table, which you have at the back of your book. So if you flip back all the way to your back of your book, you will find that there are 12.01 grams of carbon for every 1 mole of carbon. Okay, and so technically that would be 12.01 grams per mole, or you could also write it as 1 mole per 12.01 grams. Okay, so which way do we want to use it to get out of grams and into moles? That's right, we want to use option number 2. Okay, so we're going to write in 1 mole per 12.01 grams. Okay, so then that makes my grams cancel out, and now whatever this number is at this step, it's going to be in units of moles. Okay, so now I'm at moles, and now I'm going to use Avogadro's number to get out of moles and into atoms. Okay, so let's see. So I'm just going to use Avogadro's number written exactly as it is here, no flipping, because I've got it as 6.022 times 10 to the 23rd atoms per mole, right? And so then that's going to make the moles cancel out, and that's going to leave me with units of atoms. So how would you type this into your calculator? You would start with 7, you divide by 1 million, you divide that answer by 12.01, and then you multiply that answer by 6.022 times 10 to the 23rd. Okay. If I were you, though, I would get in the habit of taking any exponential number and I would wrap it in parentheses. I'll show you why in the next problem. Okay. And so once you do this, you should get, I forget what answer. Let's see what we're supposed to get. We should get, nope. So let's see. First step, we get 5.8 times 10 to the minus 7th moles. So we should get 3.5 times 10 to the 17th atoms of carbon. That's what you ought to get. Okay, let's do another example. This time we're going to start with atoms, and we're eventually going to get into pounds, okay? So the flow that I've shown you is mass to moles to atoms. But if you start with atoms, how do you get back to mass? Well, you really just go the opposite way, okay? So from atoms, you're going to get to moles, and then from moles to mass. Now let's just remember what conversion factors we use at these arrow points here. Okay, so remember from atoms to moles, you're still going to use Avogadro's number, 6.022 times 10 to the 23rd atoms per mole. From moles to mass, you're still going to use the atomic mass in grams per mole for that element. And then again, remember from the previous slide that really this gets you into units of mass that are grams. So then, like this problem, remember that we're wanting to eventually end up in units of pounds. So then there might be an additional step to get you out of grams and into whatever other mass unit the problem asks for. Okie dokie, so let's get started. Oops. Whatever. Okay, so we're going to just have green ink for this part. Okay, so again, we want to know how much that is in pounds. We know that there's 454 grams in 1 pound. Okay, so please remember that this 454 grams is not the quantity that you're starting with. This is a relationship between grams and pounds, okay? So that's usually where people trip up with this example. The quantity that we know to start off with is that we've got 1 billion atoms of silver, okay? So let's start with that number. We've got 1 billion, so that's 1, 0, 0, 0, 0, 0, 0, 0, 0, 0 atoms of silver. Silver has the elemental symbol of Ag. Okay, so we want to go, again, atoms to moles to mass and then into pounds. So our first step is to get out of atoms and into moles. And so we are going to use Avogadro's number, but this time we're going to flip it upside down. So we're going to multiply by 1 mole divided by 6.022 times 10 to the 23rd atoms. And that's how our units of atoms are going to cancel out. So once you do that, you've got your units of moles. Okay, so we want to get into grams this time. So we're going to use the atomic mass, flip the right way up. So that's 107.9 grams of silver per 1 mole of silver. And so then that mole cancels out. Hooray! And so then the last step from there is we want to not be in grams, we want to be in pounds. Okay, so we've got 454 grams is equal to 1 pound. Okay, so we want to end up in pounds, so we want to multiply by 1 pound per 454 grams. Okay, and then the grams cancels out, and whatever this number is, that gives us an answer in pounds. All right, so how would you type this into your calculator? Now you're going to be dividing by a power number, a number raised to a certain power. And so when you type 1 billion into your calculator and then you divide by this guy, you need to have parentheses around this entire number. And the ending parentheses needs to capture this exponent number, okay? So 1 billion divided by a quadrillion or a quintillion, I forget what 23 is, but 1 billion divided by a quadrillion, that should be a very, very small decimal number. But usually what people do is they will type this into their calculator without any parentheses, and what happens is your calculator interprets that as 1 billion divided by 6.022, and then times 10 to the 23rd on top, and that is not at all what you want. So instead, what you do is you do what I showed you here. You type in these parentheses, and then your calculator understands that the times 10 to the 23rd power is also supposed to be in the denominator of the fraction that you're essentially typing into your calculator. Okay, so you take 1 billion, divide by parentheses 6.022 times 10 to the 23rd, end parentheses, and then multiply by 107.9, and then divide by 454, okay? So once you do that, your ending answer should be 3.95 times 10 to the minus 16 pounds, okay? So if you're having issues with whatever calculator you're using for this course, please feel free to email me or come to my office hours, or ask a question during whatever class meeting we've got, and show me your calculator, and I'll do my best to help you sort through how to use that calculator. I would also hazard a guess, though, that there are probably a lot of YouTubers who have help videos on their YouTube profile to help you figure out how to do stuff like this with your particular make and model of calculator. And you might be able to have help with it from YouTube faster than you can have help with it from me. But I'm also open to doing my best to help you out. Okay? All right. Thanks for joining me. Bye-bye.